Hello and welcome back to Algorithm Coding in Leaf. Today we're going to be looking at a binary tree. This is a very common data structure used for storing and quick retrieval, and it's a very efficient data structure, and it should be one that you know if you're doing a lot of programming. It relates a bit to the episode we did on binary search. Binary search actually requires a flattened form of a binary tree, and today we'll be showing basically how to make a dynamic form of that tree where we get the benefits of that search without having to have a flattened array. If you're new to the show, I'm edA-qa mort-ora-y, and Leaf is my language. It's the one we'll be using today. It shouldn't matter that much for the algorithm explanation. It should be straightforward enough to understand the bits we're doing. Hello Thor, welcome back to the show. And if you have any questions during the show, please feel free to ask. We're here to learn a bit about complexity and a bit about coding. Whatever's on your mind, just let me know and ask, and I'll be sure to answer it. With that, let's start going with the code and see where we get to. I started setting up a little bit of code already, and it's very basic. I just want to get the basics done so I don't mess up the basic syntax. But we don't have a class yet. We'll be implementing this class called binary tree. Before I do that, let's draw what a binary tree actually is. We'll be using this infamous drawing program again. And I'm not so happy with this drawing program, but I don't know a better one. If you know a better one, please let me know. This is edA-qa, it's for Linux. And so a binary tree. When we create a binary tree, let's use the numbers over there. We're going to stick a 2 in the top. And then we have the second number 5. And the way a binary tree works to store this is a binary tree says, well, is 5 less than or greater than 2? Well, it's greater than 2, so let's go stick it over here. Oops, my horrible circle. I had to deal with that. And then we see the next item, well, it's 3. Is that greater than 2? It is greater than 2. But we already have a 5 there. Is 3 less than or greater than 5? It's less than it, so let's go stick it over here. And then we have a next one, 8. Where is 8? It's greater than 2. It's greater than 5. So let's go put it down here. Now let's say we come in with the number 1. I don't think I have it over there, but I'll just leave it here for now. Number 1 is less than 2, so it goes over here. Number is less than 1. We may be using integers here, but let's pretend we're using floating point. So now we have the number 1.5. What would happen is it comes in here, it's less than that, greater than 1. So you end up with 1.5. I remember why I don't do fractions, because this program doesn't let you do a dot on the screen. So it makes the fraction very hard. So now you have a 1.5. And now let's think about how this works. Is every time we have a number and it goes left and right. And if we have this well balanced, you'll see there's an equal number of numbers on each side. So say we're looking for the number 3 now. We get to here. Which way is it? Well, it's greater than it. So we're seriously looking for 3. We go down here and it goes this way. Because it's less than it, it goes this way. And it finds it. So yay, we found it. Very good. Say we're looking for the number 0. So number 0, we go this way. And we want to go this way, but there's nothing there, so we don't find it. And this creates the basic binary tree. It's very efficient for searching and insertion. Well, searching is the main reason. If you just cared about insertion, you just use a basic vector. And it's also sorted. And this is a little bit weird, is you can actually walk binary trees. And you start at the lower leftmost tree, and you say you walk here, then you go all the way to the next leftmost one, and it goes to here, and then you backtrack up, then to here, then you go down here, here, here. So they have this property of being walkable, and they can be searchable, and they're very fast in this regards, and they use a low amount of memory. And why don't we get into coding this up and see what it looks like in Leaf. And then if you have questions, again, let me know. And if you don't like my drawings, you can contribute to my Patreon campaign. That's the first thing I'm going to buy is a better tablet. And the second thing I need to do is that, well, even before that, I need to find a better drawing program. So if you know any ideas, please let me know. So here we go. Yeah, let's go back to draw. So we have that basic structure. So what do we need? We're going to create a binary tree in main. And we're going to make it a shared binary tree. Actually, let's do it this way then. I keep typing the wrong character. Shared binary tree, and we'll make this of, let's just do integers, integer. And that'll create one for us. That's the construction format in Leaf, just to that. And we want to call an add function. Actually call it, yeah, let's call add. Add makes sense. We're going to add the item to the tree. So we have to have an add function here. And this is generally how I start at a high level, and we see what it is. And this will be of type T, and it has no return value. And so how do we start storing these things in the tree? Well, we're going to need some node, and this node is what I showed, the bubbles on the screen. The nodes are there, and they have to contain a value. So the first thing we need to have is we need to have a value for it. And a node also has two branches, to the left and to the right. I'm going to say left, and this is a shared binary tree as well. And to the right is also a shared binary tree. Sorry, not a binary tree, a node. Shared node, sorry. It should be shared node. Because these are all nodes. See? Except you don't have to have a left node. So that makes it optional. And you don't have to have a right node. That makes it optional as well. So if we don't have those, then they're empty. And so the first one, and then we need some sort of root node. We need to say root. And this is also optional and shared because we might not have a root node yet. And so we deal with the easy case first. Let's deal with the easy case where we say, is there a root node? And then we say, so not has root. What do we do then? Well, then we create an item for it. But let's create the node anyways, because we always need a node in any case. So var n equals, this is a type shared node. We need one of these. n.value equals item. And I don't have a constructor for this yet. I'm just doing it this way. It's the quick way for this. Create a shared node. And in this case, if we don't have a root, then root equals n, and we can return. Let's just deal with that case first. And here we'll add it, and we'll see what happens. And we might get some funny error messages, and this is something I'm working on Leaf right now. And it actually works, so that's good. I'm getting better at knowing my own syntax, which would really help. So when a weird error message comes up, just think, all right, this is really clear, it's going to be fixed up, but at the moment they're just weird. But how do we know this worked? Well, maybe we should do a printing function at the exact same time. Why don't we do exactly that? We'll do a dump function. It does nothing but print the output. And we know there's only a root right now. And so we're going to say basically if you don't have a root, then return. Because we don't return that. Or rather, we should rather have a dump node function. And I'm going to put that underscore on here to mark it private. I don't have private modifiers in the language yet. They're coming. We have an optional, let's call this node, optional shared T. In our dumping, we're going to walk the tree. We're going to walk from left to right. And so what do we do if we don't have the node? Then we return. There's nothing to print out. And so that's why we can just simply start here at dump node root. We'll let it take care of it. And then we're going to print a line feed after it, so the individual prints don't have to do a line feed. And that just says no arguments to it. So it's just empty. We're not printing anything. Now when you're dumping, you want to dump the left side first. This is a difficult tree. So, and I'm going to use something called a getOp now, because this is an optional type, and this not says we might not have it, but if we do have it, we still have to get at the node. And I don't have the perfect syntax for this yet, so let's just do it the kind of ugly syntax yet then. So get opt node dot left, then we got to print the right left node, dump node, get up node dot left. Actually, that's silly. We already have that check here, so we just do this. We just do dump left. You just dump the left one, and then we're going to dump the right one. But we have to print the one we're on now. So we do a standard.print. And what do we want to print? We want to say get opt node.value. And we'll put a space in here as well. We won't worry that there's too many spaces. Let's just go with that. And print only takes one, so let's do 2 standard prints. Some of the standard library is missing right now. This is really a rudimentary formula language, but that should be okay. And then each time we add one, let's print it out. Let's do bt.dump. Now let's see if this works. Alright, so 28. I have an unexpected type. Optional shared T, and yeah, okay, it's supposed to be an optional shared node. And I probably shouldn't call this node because it has the same type, so let's call it N. N. Names and symbols share the same namespace in Leaf, and you won't see that now, but that's a very important part of the language because they can be used interchangeably, so I can't name the same thing twice. Alright, now so I have a bit of an error. Now I have to figure out what that error is. This is one of the ones that doesn't give a nice error message. We have some symbol here. So if I call dump, what does dump do? There's a good chance it's because of this. We have a recursive function, and recursive functions have a hard time identifying what the return type is. Yeah. Okay. So that's a bit messy. So let's first of all get rid. We'll improve this, adding item, and see what we get. 2. So we added 2, so we confirm that 2 is here. But what we had in the other ones is we don't have anything yet, obviously, because we only added the root. So we only add the root, and the other adds are just basically ignored, so you don't see anything more. So let's figure out, we have to fix add now. Let's take care of add. Where do we go with add? If there already is a root, so then where do we do? Now we're going to start invoking the recursive add procedure. And so I'm just going to call it here add node. And we're going to start at root, and we're going to give it the node to add. And we'll do this because we're going to do it in recursive fashion. And recursive fashion isn't the cleanest way to do this, but we're going to start this way, I think. I'm trying to think if it's easier to start this way or to start with the actual... Yeah. No. I'm just thinking about it. I think out loud. Sorry, I don't always go over this in my head first. Let's do it this way. And our node to consider is, and I'm going to make a consider node equals root. And we have it there. And so now we have 2 options. And we're going to make a loop here. Just loop. Or let's do a while true, if you can recognize that better. While true. And we're going to do is say if consider, so has consider.left, or rather not. If it doesn't have a left node, and actually let's consider the value first. We have to look at the value. If the item is greater than consider.value, and this is optional, so we'll say get opt. And this is just, there's a few syntax things missing right now, that's okay. So if it's greater than it, we're going to go to the right. Otherwise, we're going to go to the left. And so let's take care of the left case right now. If it doesn't have a left node, then we just insert it as the left node. Consider that left equals n, and then we return, we're done. If it does have a left node, let's not worry about that. Let's see how far that gets us so far. Node type should not appear here, 24. And something unusual I have here, sorry about that. Considers root item. Alright, now I have some weird syntax here that I don't understand myself. Well, let's break this up a bit and say greater equals. Oh, I know what it is. Sorry, never mind. I forgot my then statement. Yeah, then. Pretty obvious, but still 26 is the same issue. And 26 we still have. Yeah. Now this is optional, and this is another syntax. We can do a question dot here, and it still annoys us, so let's just do get up then. And as I work through, I'll go back and fix these up and figure it out why. Okay, so now I have another mistake, and again, I'm sorry for the error messages. It's actually the branch I'm working on Leaf right now, are how to improve these error messages, so it's not really improved. I haven't even done anywhere on it so far. Requires a shared node optional, and this is on line 27. So right here. Okay. Now it breaks because we have no condition that goes further. So in this case, we would say consider equals dot left. But that'll only handle the left case, so we actually handle the right case as well. So we'll just walk down and not add it for now. And add the right node. Okay, access unset optional. And that's fine. I mean, we haven't handled this considered yet. So we're going to do the exact same thing here. It's not get opt consider dot right. Alright, so we're fumbling around. We have the values, so we're adding 2, adding 5, 3, 8, 1, 8, and 5. And so you see it gets them in order. 2, 2, 5, 2, 3, 5, 2, 3, 5, 8, 1, 2, 3, 5, 8, 1, 2, 3, 5, 5, 8. So if we successfully added them in order, that's what we have to do. And we did one duplicate here. I didn't intentionally do that, but it's there. We don't know which 5 this is, but it doesn't matter in this case. So we now have those values in there. I'm going to see if I can do the question dot here. It should have worked. Yeah. This has, if you're wondering about this in question and stuff, this is very similar to, say, in C# if you're comparing against null. What Leaf has, though, is that shared values by default cannot be null. And so it's very strict on that. If it's an optional value, optional means it could be optional, and it doesn't let you work with that unless you've guaranteed that it's not actually null. And so that's why you have this have function. Now these explicit checks for has, they're supposed to be uncommon, but data structures are more common, and I'm more likely going to find a syntax that makes this more satisfying, because in particular, the moment we've established we have a root, which is right here, I don't want to have to continually recheck, well, this is a root, get up, get up. There should be a way for us to say, okay, fine, we already have this, let's go on. And, I mean, this would be, we can actually do this way then. We can say, we could actually do this. We say get up root right here, and then we know we have an actual value. It's already removed it, so we can get rid of all of this here. We can get rid of all the question marks because we've already determined that we have a root. We still need to say has. So consider is never optional. So what we've basically done is said consider is not optional. And that should do the same result. Whoa, mismatch optional, what did I do? Did something wrong. Yeah, and down here we have to undo it on these ones as well because those are, we've determined that they're not optional. And what I'm kind of missing in the language is that I do have a way to deal with optional values, but when you have to do it in a syntax like this, I don't really have an easy syntax to do that as to mark it together. But in any case, that's not the focus of it. So we created this, and we see it, we have the tree, we have that sorted list. This is the basic of the binary tree. We don't really know what it looks like in this form. It's what we drew before, but this dedumping function doesn't really show that. Well, if we wanted to, in a flattened form, we could show it a bit better. Let's do it in a flattened form. I'm going to put little braces around these, standard prints. And this way we can see what the tree actually kind of looks like, very roughly. Alright, and it's kind of messy. I should have had a space after it. Sorry. There's probably a space before. Yeah, we have lots of spaces, but you can almost sort of kind of see a tree in there. Drawing an actual tree is rather difficult. It's a nice programming problem, but drawing an actual tree is rather a lot of code on the command line. So just trust me, I'm going to just remove that for now. It was kind of messy. But let's look at first the adding, and let's make one more function. We want to do a find first. So let's make a function that says find out here, and it's going to take the tree as well. So we'll give it a tree, and we'll give it a value to look for. And we'll make a find function in the value there. So this is actually item. We called it item before, so let's do this. This is of type T. And for now, we're going to make it return an integer. And we'll make it return an optional integer. If it's founded, it's going to return the integer of its index where it is. Otherwise, it's going to return nothing. It's going to say, I don't have it. So here we're going to do result equals bt.findValue. And we can write this out here. We're going to do standard.print line. Let's just do print for first. I'm going to say, actually print, yeah. Looking for value. And now we'll do the if. Now we can say that if it has, because it's an optional again, if it has a result, then standard print line, this is supposed to be print line as well. Or let's just make it one line, doesn't matter. Print line found at get opt result. Okay. Now this is where the optional is. Let's just actually change this. Let's not do the result this way. Let's do it this way. Found at. And let's pretend if we have a result, we'll write the result, or we'll write -1 if it didn't find it. And by default, this is going to return nothing because we haven't returned anything yet. So let's find bt. Let's look for the value 3. Looking for an integer found at -1. This is correct. I'm going to take this other dumping off here now so we see it. The reason it says -1 is because we haven't implemented find yet. And by default, the return value is going to be unset because it's optional and we didn't give it a value. So down here, when we say standard print line, we say result or -1, it says, well, we don't have a result, so let's print -1 instead. Ideally, we'd print something else entirely different, but I want to show you how an optional can work there. So now we have to go through this node and look for these items. So we're going to start at the consideration node again. We can start with basically, if you don't have a root node, then you can just return. And you don't have to return a value. Because the return value has a name, it's implicitly defined to its default. Otherwise, let's start looking. And we're going to do the same consideration structure. Consider equals get opt root. We'll start at this point here, and we're going to do while true. We'll do the same looping to find, and it's a very similar strategy to the one adding. So actually, let's go up to there, dumping, or adding, because it's a very similar structure. We have one additional one. If item equals consider.value, then we can return, but what? Actually, this was really stupid to return a optional integer. I was thinking of binary search. All we can return is true or false. The default is false, and we return true here. And so we might as well say, did we find it or did we not find it? So result, we're going to say yes or no. It's probably going to an infinite loop now if I do this. Yeah. So I have to finish this. So in this item here, if we found it's true, otherwise We'll do the exact same thing. Item is greater than consider.value, then we're going to the right. Otherwise, we're going to the left. If we don't have a consider.right, then we return, we're done, we don't have anything. Otherwise, consider equals the consider right node. If we don't have a left node when going left, then we return. Otherwise, we do consider.left node. And we keep going until we have found the node we want. Looking for 3, yes, I put a space in there. Found. Looking for 3, found, yes. So let's find something that's not in there. The value of 10 is not in there. Looking for 10, no. And this is where 5 is interesting, because 5, it has multiple copies, but it can only say yes. And let's take the leftmost value. We know its leftmost is 1. Yes. And to be verified, let's find the rightmost value, which is an 8, and that should also say yes. Just make sure we're not doing something weird. Let's look for a value right in the middle that it doesn't have. Found 4, no. And this is what we expect. We have these in this tree now. And we've constructed this binary tree, and we searched it, and it has a searching, and we have the adding to it. Now let's draw out a tree once again to show what's actually happened here. And we'll use the real values this time. I'm going to make this a little bit smaller so I can see what we're doing. I'm just drawing on top of the background here. I want to see all the values here. We don't need the second 5. We can get back to that. So what are we doing with the value tree again? We're looking for, we're in main, we're doing the adding. So the first one we added 2. And remember the code said we don't have a root node yet, so it's going to set the root node. And we're going to have a value 2 in that root node. And then we get down to 5. What we said again is that 5 is greater than 2. So we put it off to the right. If I'm really slow, it can almost be legible. And then we added the value 3, which is greater than 2, and it goes down here. And this is what our algorithm was doing again. And I'm just trying to redraw the tree. 3. And then we added an 8. I should probably draw the 8 first before the circle. 8, and then we added a 1. Now, we added another 5 here. So what happens when we add another 5 and we get a duplicate? We get down to this 2 here. Well, it's greater than 2. And consider very carefully what happens when it hits that 5, though. So we get down, we hit the 2. It has a root through down here. It's greater than 2, so it goes down here. Now, when it gets to the 5, it's not greater than 5, so it goes to the leftmost branch. So you get to the line here, and you're now at the 3, and it says, well, it's greater than 3, so it should go off to the right. We don't have that yet. And this is one of the dangers of an unbalanced tree. And this is, if we don't balance this, you get weird stuff like this, where the 5 is actually not connected to the value where it's at. And it can balance this, but we're not going to do balancing today. We can take care of that next week. What we want to look at now is what is the potential problem for this, or what is the time complexity of the things we're doing. So if we have this tree, let's consider this carefully now. This add function. The add function, wherever I have it, add, it walks through the tree. Now, if we had an ideal map, you would think, well, each branch holds the same weight. And that's ideally when we have a balanced binary tree. So if this were balanced, which it's not, I had to get my character again. My favorite character of theta. If this were balanced, we'd have a theta of log n. because each step of the way we prune off half the tree until we find it. But what's the problem with an unbalanced tree? Unbalanced? And this is where the scary part is, it's n. Because think about what happens if I clear this again. If we add a whole bunch of numbers in order, we add the number 1, then we add the number 2. Now we want to add 3. Well, it's greater than 1, it's greater than 2, so we're going to go down and add a 3. Now we want to add 4. Well, it's not greater than, it's greater, now it's 4. You can see the problem forming here. This tree, if it's not really a binary tree, if we add something in order, it degenerates. And it takes n steps to figure out where it is. It goes 1, 2, 3, 4. And this keeps happening. When you add numbers to order, in order, it keeps taking the longest possible path. And this is why my unbalanced tree is actually theta of n. Because it actually takes n steps each time. Now, if you added another value, if you added 0, it would only take 1 step. But without the balancing, it's theta of n. What we do have, though, is, so this was time complexity. Put a star here instead. Time complexity. What about space complexity? And here we're going to be better think about the algorithm as a whole, not the one. Let's think about the collection itself. The space complexity is, well, we have these nodes, and we only ever have to create 1 node per item. Even in this degenerate case, we only have 1 node per item, so the space complexity really remains as theta of n, which is good. For most of your collection types in programming, a theta of n for space complexity, this is good. You're not taking more memory than what you put in. At some point in the future, we can actually get to the data structures where this is actually less than n. There are data structures where you have a less than n, and those tend to be the radix tries. They're a bit more complicated, but we will get there, and binary tree is a good starting point for that space complexity. And so adding, we have these two adds. It could take in worst case n log. And if the tree was actually balanced, if it was questionably balanced, we'd have theta of log n. And if you had uniform data distributed and you inserted it like that, you'd actually stick close to this. So this is where you tend to have something called average case complexity. Even on an unbalanced tree, the average case complexity is going to be theta of log n. Now, if you've heard the term amortized before, be very careful. This is not amortized. Average case complexity means if I take all the possible inputs, everything I'm going to add into the node, what will my typical complexity be? What will the average complexity be? And in this case, it's going to be O log n, based on the average case being a randomly distributed value. Now, average case is a very kind of, it's a dangerous sort of time complexity measurement because it requires a lot of conditions. It requires your data isn't degenerate. Quicksort is another one that's commonly noted as average case time complexity of n log n, where it actually has a true complexity of theta squared, because some degenerate cases for quicksort become n squared. Not n log n, but most of the time we say n log n because we don't have many of those degenerate cases, but they definitely exist. And that's the same case with my tree here. They definitely exist. The other one that's so commonly, that's always noted as average case is a hash map. Hash maps are often quoted as average case complexity if they add function of 1. And that can only be in the case of an average case input where you have perfect distribution and you have a perfect hash and everything's beautiful. But otherwise, a typical hash map has a very degenerate case, usually log n or even n sometimes. So just be aware of this, the difference between average case and if you've ever heard amortized. And if we're being strict here, the time complexity of this function right now as it is technically theta of n. It's going to take n steps in the worst case. And again, remember we're always talking about worst case here, and this is really, when you talk about complexity, this is where it gets really confused because we talk about average case and worst case, but there's also an average worst case, and you just kind of have to deal with it. So let's say this is worst case. Actually, I'll put it right here, worst case. And we'll say average case down here. And what about best case? We might as well put this, if we're taking only the best case for any input, what's the best possible case we have? And this gets really weird in a tree. It's 1. Our best case is the tree is empty, and you're inserting the first value. And so this is why I say these best cases and average cases, they give you random, you have to be very careful using them. That's why we always usually consider the worst case. Worst case is like, look, it's not going to be worse than this. Like, this is n at the moment. And we know if we modify this tree, we can get theta of log n. But today we're not going to do that. Today we're going to just analyze this a bit more. And let's go down to the complexity of find. Because find is very similar, it ends up having the exact same complexity. Find complexity is same as add. Because it's doing the exact same operation. And I would actually refactor this tree. This is small, the code, so I wouldn't worry about it right now. But in some data structures, what you actually may want to do is you may actually want to make the add function call a variant of find. So you look for it first, and then you add it. And you find the closest node. But we did them differently, and that's why we had the exact same time complexity as add. This is unfortunately theta of n if it's unbalanced. If we balance it, it'd be log n. So these are all theta of n. And this is where dump should not surprisingly be that when we have this many nodes, we have to output each node once, so it should be a theta of n. There are a lot of ways to do dump, and we've chosen kind of an optimal one in terms of time complexity. But what about the space complexity here? And I choose this one because we have this recursion again. You notice dump node calls dump node. Whoops. Now let's pretend for a moment that this is a balanced tree again. So each node has an equal number of nodes on both sides of it. So we'll say if it's balanced, what is our time complexity of the balanced tree, or space complexity? And when counting space complexity, as I mentioned last time, you can basically count each recursion depth as 1 because that's your dominant force here. Each call the recursive function was considered at 1. So how deep does this go? In a balanced tree, this goes down to log n because that's the depth of the tree. And maybe this is actually an interesting function to write. For example, let's write an actual depth function. Define depth. And we'll do it the exact same way as the last one. We'll do a recursion approach and optional shared node. And the depth is the depth from the top of the tree to the bottom of the tree. Like, what's the longest path? And this returns an integer. And so the depth of this tree is 4. 1, 2, 3, 4. And the depth of a balanced tree would be 3 in this case. So if we had another tree, let me draw a few circles without values in them. So you had a tree like this. This would be a depth 2, and this would be a depth 3. And this depth is better than this one, all it holds just many values. At depth 2, you can actually hold up to 7 values. Worst case, your depth will be 7, but you could ideally have 7 values. So let's write this depth function because it's a very common statistic. We're going to return depth node of root. So if we don't have the node we're looking at, then we return 0. There's no depth here. Okay. Otherwise, we're going to take the left depth. Left equals depth node get opt n dot left, and the right node is depth node get opt n dot right. And these will return 0 if there's nothing there. And we have the 1 for the current node, and we want the maximum of those. So left is greater than right. I don't have a maximum function yet, so excuse me on that. Actually, let's just write one quickly. Let's write a maximum function. Would be, yeah, Sasha, we're doing graphs. I love graphs. Graphs are my life. So if we have a greater than b, actually we can just return directly a greater than b, then return a, otherwise we return b. Okay, and so this lets me simplify up here and do return max left comma right plus 1, because don't forget the current depth, otherwise you'd only ever have 0. Now let's print out the depth of our graph. Depth bt dot depth, I think I call this a depth function. If I wrote that right, we'll just leave the graphs on the screen. No, I wrote something wrong. Something wrong with my depth function. Why doesn't it like my depth function? Oh well, actually I have to use functional notation. Sorry. So the depth of 4. And that's bad. We have 6 items in the graph and it's a depth of 4, where we know a tree of depth of 8 items could be of depth 3 instead. If we rearrange these items and perfectly balance them, 3, 5, 8, 1, 5, and reduce the duplicate one, we still have depth 4. Let me think about that. 2, 3, 5, 8, 1. Yeah, it seems a bit weird. And, we should probably put the 3 and 2. I was trying to show you how it changed the depth. So now we have depth 3. And so you notice by rearranging the numbers, we can reduce the depth of our tree and make it more efficient. And we can do this next time and show you how this is done automatically as adding. It's something called balancing. And in the balancing in binary trees, you really want a balanced tree. If you have random data, you can sometimes get away without it. Or you can simply check the depth sometimes and say, look, my depth's okay, I'm fine with this. But, as we showed, let's actually dump the tree again, so bt.dump. It's the same tree, it doesn't matter what order you're in, it's the same tree, 1, 2, 3, 5, 8. And we can add even more items in here. For the dump, yes, I'm visiting all nodes. In the dump, I actually go to 1, 2, 3, 4, 5, the dump. And for the find, no. For the find, we're actually doing the binary search on that. Now, we should be able to cram even more things in this tree without saying... So we should be able to stick a 6 and a 7 and wearing a 4. Let's see if we can keep the depth under 3. Now we put the depth 5 because we put it in a weird order. But let's, for experiment's sake, show you how bad this can actually get. If you add all of these numbers in order, 3, 4, 5, 6, 7, 8, 9, 10, we add all of these, or we can just stop at 8. This is the worst possible way we can add them, and we have a depth of 8. Our search still works, it just takes longer. And so again, this reinforces the need for a binary search, or a balanced tree. So we'll go back to our first list where we had 3. And we'll get to balancing again next week. Balancing involves a bit of rotation. It's a bit more work, but it'll work. Now let's go, we have depth. Now we want to say, what is the space complexity of dump node? And again, if this was balanced, it'd be log n, because it goes through one depth and backs out. Unfortunately, in an unbalanced tree, the space complexity is n, because we have this linear arrangement again. If they're all down in a line, you have to go the depth. The actual depth function actually indicates what the depth of dump node is going to be. How far does it have to go down to dump it? And I think that's it for the binary tree today. We've covered the basics. We show how to construct it. We know the time complexity of it, space complexity. And right now, because it's unbalanced, everything is basically theta of n. Everything is going to take this many operations. It kind of sucks. We want to get to log n. We'll do that next time with balancing. and we showed how to find things in it, and we showed how to dump the node, how to walk through a tree. This dump node is actually called something called walk, and that's something we could probably do instead of doing dump, because dump is very sort of, this isn't so helpful. It's not a general purpose function. What if we wanted to sum the values up in the tree instead? We could do something else. So instead, instead of writing dump, let's write a walk function, walk. And walk is going to take a function as a callback. And this function is going to be a bit weird. This function is going to take the item of type t and return nothing. And walk itself returns nothing. And we're going to do walk node at root, and we're going to pass it f. So we're passing a function now around, and I'll show you this in a second. So it's going to be basically the same as dump node. So I'm going to copy from there. I'll copy the whole thing. We'll do a walk node. If there's a walk node, we do nothing. Otherwise, we return nothing. But we need this function, item of t. And I'll put this on a new line since my view is really small and I have big fonts. If we don't have the node, otherwise we do a walk node, we do it recursively. And instead of calling standard print, we're now going to call function on it. On that value, we're going to call function on it, whatever that function happens to be. Now, we haven't actually... Okay, I don't know what happened there. My browser's still... Okay, and I have an error on line 103. Oops, I have this backwards, f comma root. 103, walk node, optional shared. What have I done wrong? Trying to think, I might not be able to do this if I did something wrong. Converting from integer blah, 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 to... Yeah, I'm not clear what I did wrong there, actually. Oops. Clear that. Let's get a better expression of it. It's saying I'm converting the wrong types in my function. Again, this is the horrible error message. It's the branch I'm currently working on Leaf right now, is to provide better values or better error messages. And I'm just trying to wonder what I actually did wrong here. What do we do wrong? Item t... yeah, I forgot this part. I have to say what type of function it is. You can never have half a function there because that's not a function type then. It's the arrows, it's not the params, it's this arrow in Leaf that defines something as a function. Okay, I still have an error, but this isn't line 110 now, that's okay. And I forgot to pass f down to the next values. So we haven't used this yet, but now we have this generic thing. Walk does nothing but walk through the nodes in a defined order. And sorry about the noise outside, there's some children around making noise on me. I don't know if you can hear it. There's lots of laughter. And so now, dump we can define a new way now. Dump we can instead define as, well, let's make a function that walks through all the items. Standard.print item, standard.print space. And then we'll print the line at the end. Okay, and you notice the printing is the exact same now, but now instead of having a designated walker for dump, we have a generic walk function. This walk can do anything we want it to. It just says, I'm going to iterate over all the values in order and tell you what the value is of it. And then in dump, all we do is dump is actually prints out the values. And we can write helper functions this way as well. We could, for example, down here, let's write out the sum of this. This gets a bit more difficult. I'm going to say var sum equals 0, and then bt walk, and let's give it an item. Sum plus equals item. So this is like a fold operation. Our other things had fold operations as well. And then right afterwards, we can say print line sum. Now we get the sum of the values as well. So we have sum 19. And we're using the same walk function. This walk is a generic purpose. It walks through the tree in order, and it prints out the values. And we'll see that a lot in functional programming when you do these types of things. At a high level, if you had a sum, you'd probably want a sum function, but these walks are like the basic building blocks of data structures. They're very convenient. When we did our linked list, we had a fold function as well. Now a fold on a tree is a little bit more difficult, so I won't write it today. But you could do the same thing here. It's less common to need on a tree as well. It's very infrequent you want to fold over the items of a tree because it's sorted and it's untypical. Even sum is a bit untypical here, but I decided to do it to show it how it works. But walking through the tree is very common. And you would also have a reverse walk if you want, like a rev walk, and you would just walk the other way. You'd do right and then left instead, and that would be a reverse walk. And okay, I think that covers it. And so the time complexity of walk is going to be the same as dump. So I hope you enjoyed the episode on binary trees. I will follow this up with one about how to balance this tree. As we said, the worst case right now is not so nice. So I'll make another episode, perhaps next week, I can't guarantee, about balancing this tree, and we'll show how, as you add values, how you can keep the tree in balance and then calculate the complexity on that. It doesn't affect most of the functions, basically only add. And then next week we're going to also add a remove to the tree. Now removing, I didn't do it yet because that also basically involves the same rotation operations. It's about the same complexity as adding is. And so that was my show today. I'm glad you watched, and if you have questions about this, feel free to post them to me on Twitter, and be sure to follow me here and on Twitch and on YouTube if you want. I try to answer comments, and if you have a topic you want covered again, please feel free to let me know and I'll get back to it. If you're up for it tonight, later tonight I'll be doing my next episode of Evening Rust, and we'll be done with the practice. I think we're actually going to go into one of the competitive games and actually try to start scoring some points tonight. And that'll be tonight, probably at 11 I'll start. And until then, thank you for watching, and I hope you enjoy the show. And then until next time, thank you very much.